thank you very much for coming. So the idea of this, let's say, lecture is that we present how large language models as one of the main drivers of artificial intelligence, how they work in digital humanities, how they work in general, and how they specifically work for digital humanities. So if you allow, I'll first present myself. So I'm the head of Machine Learning and Language Technology Lab at the Faculty of Computer Information Science, University of Ljubljana. We are doing research in large language models and linguistics, digital linguistics, ever since 2018, when this was not even called large language models. But so we built several LLMs for many less resource languages, including Slovene, of course. And we did some basic research, let's say data representation, knowledge injection into LLMs, cross-lingual transfer, and explainable artificial intelligence, and many applications, I mean, many of them in linguistics, but also readability, summarization, things like depression, grammar correction, folkloristics, politology, historiography, and so on, right? So I will try to share a little bit of that with you, our experience in that area, because as I will show you, basically, I think that AI is changing how we do research in general, and to some way we want this AI also to integrate the knowledge from these areas and to help us as scientists to build, let's say, better tools and better methodology. So yeah, that's the point. So the contents I'm going to talk about, I will first present large language models, how they work, and then I will speak about some of the, let's say, more recent technologies and developments which can help us in applying this methodology in different research areas like LLM agents. I will present Slovene large language model called GAMS, which we have built and which is, of course, important for everything we do in Slovene because it's state-of-the-art in Slovene. And then I will see as we basically progress in using LLMs, all these areas which are now using LLMs are in a way getting the empirical knowledges. I mean, they are getting empirical sciences, right? So if we want to work well in empirical sciences, then we also have to know some of the statistical properties and analysis which will help us to do that in a scientifically sound way. And I will conclude with the explanations and why they are hard, and that would be basically the outline of my talk. So let me start with the really basics of the idea of AI as it's currently perceived. So AI currently is based on neural network, on deep neural networks, and the motivation for that are basically artificial neurons, right? So as you can see in this picture, one cell, let's say neuron in the brain is basically a cell which has on the input it has dendrites, and as these dendrites get excited, they get information from other cells, or let's say from the sensors in our eyes or ears, wherever. And when we have sufficiently large excitement here on the dendrites, this cell produces the electrical current, and it sends that signal over this single output called axon, and these axon terminals are connected to the dendrites of other neural cells, right? And so, for example, if we get a strong excitement signal, like for example, we see a looming danger in front of us, let's say a bear approaching, then this cell will send a strong strong current on its axon and inform all the other cells, and something terrible is happening and we will react, right? So that's basically I mean, computationally, it's a very simple analogy. So we have these inputs, so this axis, right? Which are coming from other cells or from the inputs, let's say from the sensors. So each of them has its own weight, so they are not all equally important. Some might be more important, some might be less important. And then we multiply this with the weights, sum them together, and if the sum exceeds some threshold, like here, then we have the output. Let's say the signal is 1, otherwise the signal is 0. That means no signal, right? So a very simple computational model. Of course, that's one neuron, right? But when we integrate this neuron into complex networks so that they inform each other, that they can learn different patterns, they can recognize these patterns, right? So the knowledge is in these weights. So these weights basically determine what is important, what part of the patterns we want to recognize. And there's like a theorem saying that basically we can approximate any continuous function to an arbitrary degree if we have large enough network. So computationally, it's like a strong computational engine, not a single neuron, but a network. So, and how do we learn? How do we train these neural networks? So there's an algorithm called error backpropagation, whose idea is relatively simple. So we put initially these weights. Oh, the knowledge is 0, so we put some random weights on these connections. And then we see what we put, for example, the image of the bear on the input, and then we see what goes on the output. So the output is probably not correct. And then we go backwards and correct all these weights so that the output is as desired, right? So that the output fits what we would expect here. So that's the idea. And that we need, of course, lots of data if the network is large. We need lots of images. The network has to see it several times. But yeah, for this algorithm, which propagates the error backs and corrects the weights, so in 2024, Geoffrey Hinton basically received the Nobel Prize for the physics, basically, right? Because neural networks are now really important in many, let's say, natural sciences, but also in the humanities, as we will see. Right? So we said deep learning. That means that deep learning means that this network is deep. That means that it has more than one layer here, more than one hidden layer. And nowadays, neural networks have hundreds of layers, right? So, and deep learning, I mean, why it's useful is because it learns hierarchical representation. So let me illustrate this on this image. So, for example, let's suppose that we have images of different objects and we try to detect them, what is on the image. So, for example, cars, vases, animals, and so on. So if we look into the neural network, which is already trained, so and see what this network recognizes. So initially, at the early levels, of the network, we recognize pretty crude shapes, like color shapes, some, let's say, proxies for the lines, proxy for the line segments. As we move to the middle of the network, then we recognize and detect more complex shapes, let's say, almost some, let's say, again, proxies for some shapes, like circles, more complex color patterns. And when we go to the end of the networks, we recognize almost complete images, like a big here, hive here, and so on, right? So as you see, I mean, in the image recognition, what people were doing, let's say, 15 years ago, they manually tried to construct the features which would be important. So, for example, parts of the images, lines, shapes, and so on. Now, this is no longer necessary, right? So we network automatically hierarchically builds these detectors for different shapes, right? And that goes for everything, right? So we can use the same analogy also in language. So in language, we start with the, let's say, if we put the letters on the input, then we will first build morphemes, syllables, and then we will move to the syntax layers, and eventually we'll get to the grammatical layers and pragmatics and higher levels of understanding, right? So, and that's basically the main thing why we use these neural networks, because they simplify what we had to do previously to make things, to automate things, to generate things automatically. Okay, so if we move now to the language model, which I said is the main driving force of AI recently. So if I start with the distributional semantics, so that's basically what lies beyond the large language models. So it all started in linguistics, right? So Freud said that you should know a word by the company it keeps. That means a sort of the meaning of word is its distribution, right? So the company it keeps. And pretty much the same from the Wittgenstein. So the meaning of the word is its use in the language. That means that from the language, from its use, we can basically derive the meaning. And this is exactly what we try to do with these large language models and deep neural networks. So what is a large language model? So it's a very simple computational engine. So we have a probability of a sequence of words or characters or sentences, and we try to compute its probability, right? So a sequence of words, how probable this sequence is. Now, where would that be useful, right? So, for example, in machine translation, if we have two snippets of text, like high winds tonight and large winds tonight, then because the first one is more probable, then the machine translation, which includes large language model, will basically say, okay, this is preferable. I will use that in English instead of the second one. So so basically in the principle, this is the unconditional probability, just the probability of the words. But as we compute it, we typically use the conditional probability. That means that we compute the next word in the sequence. That means the word which is next, given the previous words. So for example, they attended an international conference, event, whatever. So that means that when we train large language models, we have lots of data available, because any sentence we take from the text, wherever, on the internet, from the books, we can take the sentence and then predict the next word, and the next word, and the next word. And these are our training examples which we put on the input of the neural network so that it can learn the weights, right? So that's the idea. So nowadays, we use more complex architecture of neural networks. It's called transformer architectures. So it's fairly computational, but in the essence, it's still the neural network I showed you previously, right? So, why it's complicated? Because it has, let's say, many computational tweaks so that it can be run very efficiently on the graphical processing units, which run in parallel. Thousands or tens of thousands of processors run in parallel so that they can be efficient enough for these huge large language models which have billions of parameters, right? So, I will not go here into detail, but it makes sense that you know that this is basically the only architecture which is used nowadays in deep neural networks. There's one thing which I want to mention in this transformer architecture, and that's what is called attention, right? So it's a sort of innovation which made this architecture really used everywhere, right? So let me explain this attention. So when we put the text through the transformer, so in the principle it was the encoder-decoder model. That means that if we put the input, let's say the French sentence which we want to translate into English, so it will first go to the series of encoders which will build its representation, right? So as we saw for the images, it will build its representation from the basic forms to the syntax to the semantics and so on. And here on we will have a good representation of that sentence. And now we start decoding. That means we start producing the output in the target language, let's say in English. And again, we do it through a series of the decoders, but each of them has available this representation from the encoder. And then we produce one word at a time, and then the words which are already generated, we put them back on the input of the decoder, right? So that's how the transformer in the principle works. Now the attention, which is the crucial innovation, is this what is passed on here. So here it's passed on the attention. So let me explain what attention is. Let's use this simple sentence like, the animal didn't cross the street because it was too tired. So if we have a look at the it, right? So what is its representation? So if we peek inside the neural network, we see that the representation of this it is mostly built on the animal, right? So the animal builds the core of the representation for the it. Also some other words contribute, right? So, but this attention is basically applied to every word. So every word is informed by every other word to get its good representation, right? So for example, animal will get some information from D and from it and from all the others and so on. So for example, if you would have a sentence like, the animal didn't cross the street because it was too wide. So then probably this it would be, the street would inform it, right? So not the animal. So what we have here is a representation of one attention heads. But in, let's say in the neural network, we have 10 or 20 or 50 such attention heads. That means that we can concentrate on different levels of the meaning, of different connotations, of different conditional probabilities, something which is even beyond comprehension, right? Because we don't usually think in these terms when we construct and try to understand language. Anyway, so it's something which is really useful, and how it works. So when I have the sentence, like arrive at D, all the words inform each other what their meaning should be, right? And then this goes level by level. So they inform each other, build this hierarchical representation. And then when we start decoding, then all these encoder provide information, again, level after level, and building representation for each word. So from the previously generated words and from everything available on the decoder, on the encoder, right? So, and this is the crucial innovation in the transformer, because we really get very rich representation, which is enriched to the hierarchy of the levels, right? So yeah, so nowadays we have this transformer architecture basically everywhere, not just in the large language models, but we also have it in music, where these words are basically MIDI pitches and pauses and velocity. We have it in object detection images, where part of the images are the words which we construct in more complex parts, or the pixels. So, and in time series, for example, we compose the signals, let's say the hard signal or any other signal, and so on, right? In tables, we can also use it to construct this self-attention to get more rich representation in tables, and so on. So we call these models, which are built in such a way, as sort of foundation models, because we train them on the task, which is, let's say, even if weakly related, but it contains lots of knowledge about the given area of research. So for example, in the text or in large language models, we know we take just the whole internet, everything there is. If we want to build a specific foundation model for the medicine, we would mostly concentrate on the medical text, or for the literature, or for the folkloristics, or whatever we want to deal with. So yeah, so how we process LLMs for text. So learning goes in two phases using this transformer architecture. So the first phase is this pre-training. So we predict, let's say, the next word, or we mask certain words, and so on. And we need huge amounts of text, so everything we can get, right? And then the training is pretty long. It requires basically supercomputers. But yeah, now we have captured everything about the language. And in the second phase, we can be much more, let's say, we don't need that many resources. So in the second phase, we do what is called fine-tuning or prompting for a specific task. And it's much faster than the first phase. If we do fine-tuning, then we need just some specific data for that areas, because the general knowledge and the language, that is already captured in the neural net, right? So, so there are nowadays many pre-trained transformer models available, and also multilingual. We use them in everyday life, and there are also models for less resource languages such as Slovene, which I will speak of a little bit later. So in general, we have three flavors of these transformers. One uses just encoders. They are used for text classification. They are typically fast, and yeah, so we can use them even on relatively cheap computers. Then we have the ones which I showed, encoder-decoder ones, which first encode and then decode. Typically, this is used, let's say, for machine translation. And the more, let's say, recently popular approach is we use just the decoder. We just generate the text. For all these generative models like ChatGPT and so on, they are architecturally, they are decoder models. So encoder model is BERT. I mentioned it's used for text classification. There are many such variants. Many are publicly available, including Slovene. We have built several of these models for many languages. So if you want to use them for text classification, for example, detecting the sentiment, deciding if something is relevant for us, comparing two text, we use this type of models, so BERT models. These models can be multilingual, of course. That means that they can be trained on several languages at once, not just on one, but on many. And to some degree, they enable what is called cross-lingual transfer. That means if I take a pre-trained multilingual model, let's say, and specialize it on English data for sentiment detection, what is the sentiment of the text, whether it's positive, negative, or neutral, then I can use the same model because it was trained also on Slovene. I can use it on Slovene as well. We will lose a little bit of accuracy, but it will still work very well, right? So we call this cross-lingual transfer, and to a large degree, it solves the problem of insufficient resources for many, let's say, less resource languages. Okay, so let me illustrate that. So if we start with the pre-training, large language model is in principle, the data is stored in matrices, so we will put the neural network information into the matrices. We will train it on huge amount of different texts from different languages, different genres, and so on. And then we will train the network, and it will become a multilingual model, right? So now if I want to specialize it, that means fine-tune it for a specific problem, what will I do? I will take this matrix, right? And then I will specialize it with just, let's say, just Slovene data and just the news, because I want to know what's, for example, the sentiment in the news. Or just for the English, whatever language I want. And then when I have it specialized, it's still multilingual, but now it's a specialized for one task. And then I can basically use it, for example, in classification. I take this matrix and apply it to either English or Slovene, and it will still work, right? So that's the illustration of cross-lingual transfer. So nowadays we mostly use what is called decoder-only models. So we all know these names: ChatGPT, GPT-4, 5, and so on. But there are Gemini and so on. But there are also a lot of, let's say, open source models which can be easily adapted for different scientific purposes. They are freely available, and they are very competitive on specific tasks. So they're around 1,000 times smaller than these commercial models like Gemini or ChatGPT. But they are very competitive in the task which we specialize them for. So that means that they are very suitable for open science, right, to be sure. So for example, the names which are maybe interesting for us are European models like Mistral and Mixtral, which cover to a decent degree also Slovene. Chinese models, maybe not so politically interested, but pretty good recently, let's say Quen and DeepSeek. And then we have Slovene model GAMS, so generative model of Slovene, and also, for example, EuroLM, which covers all the European languages. So these models are so-called autoregressive generators. That means that they are just decoders, and we put the question, we put the prompt on the input, and only then we start generating the output. And this output is, as we showed before, informed by the attention on all the previous words, on all the prompt. That means if you want to have a good representation, if you want to have correct answers, we have to provide the necessary information in the prompt, right, nowadays. So that means that the prompts we typically write are way too short. They don't give enough context because we don't have energy and so on. But there are many tools which basically allow us to build this prompt automatically or expand them automatically to add additional snippets of information on the input. And if you want to use that efficiently, that's the way to go, right? So we have to make good use of them, right? So yeah, of course, we have these huge generative language models starting with ChatGPT in, let's say, November 22, which basically, besides just this pre-training, they're also specialized to know, to follow our instructions. So to be a chatty, to know how to solve different tasks. Let's say we say translate, summarize, write an essay, whatever, right? So if we want that they know this task, we have to train them with what is called instruction following. We will build tens of thousands or hundreds of thousands of questions and tasks of different genres, of different types, and basically then these models know how to answer this type of question. And the third phase is called preference adaptation. So that means that they are not just knowledgeable, but they have to, let's say, adapt to human taste, right? So that means whether we want to have long answers or short answers, whether they are polite or impolite, or whether there are some questions we don't want them to answer. For example, I don't know, in Slovene we don't want that they answer some culturally sensitive things like who is the better in football? Is it Maribor or Olympia or whatever, right? So there are some tasks which we want them that they are also culturally sensitive, and we do this in preference adaptation phase. So two additional phases beside pre-training, and this makes them, as I said, really useful for many different purposes. They have definitely huge impact for all the writing professions, including science and teaching. And there are many of these models. I will not go into the details, but probably the largest one and commercially the most successful are, let's say, GPT, Gemini, Claude. But we have also lots of these smaller, very competitive models if we specialize them. For example, I mentioned a few of them already, right? So the new thing which comes with these huge models is also prompt engineering. So now we no longer have to adapt neural network for each task specifically. They are large enough to answer based on their parameters only, right? So we call this design of this instructions we call prompt engineering, a sort of new thing, new discipline, which is still developing, and we basically can use LLMs for many tasks. It's a sort of prompt engineering is a sort of, the aim is to design robust and effective prompts that will interface with LLMs and also other tools. So in prompt engineering, we don't have to just rely on the knowledge already in an LLMs. We can instruct LLMs to go and fetch the answer, let's say, from the internet or from our own internal database, which we have. Let me just point you to this promptingguide.ai. So if you're interested in more about knowing about prompts, I think this collects quite a lot of useful approaches and design techniques. So I don't have today the time to go into the prompt engineering. It would require basically a separate lecture if you want to go into that. So, but yeah, there are also recently many new ways to train and use LLMs. So the first one is, okay, let's have some additional data. For example, I'm a historian. I know what happens in a certain period. And then I can specialize my model. I say that I fine-tune it for this specific problem. So if I have additional data, that's probably the way to go. Then there are many prompt engineering techniques. And for example, we also have things like in-context learning, where we basically prepare relevant context and put it on the input of the LLM. So for example, we instruct LLM, okay, I say, these are useful examples which I know how they are solved. You should solve the new ones in the same way. So it's called in-context learning. And a technique which is really useful is so-called retrieval augmented generation. That means that when the LLM gets the answer, it knows, okay, I don't know everything, I hallucinate. So why wouldn't I get some additional help from the database? I fetched relevant pieces of knowledge relevant for that question which I have here. I fetch it from the database, let's say Wikipedia or my own database. I put it on the prompt and then I only answer, right? So that, of course, hugely decreases the hallucination of large language models. We have in the reasoning, we have things like chain of thought reasoning, where I instruct LLM, don't do it everything at once, split it into the task. So that's a very common problem-solving strategy we humans use, so let LLMs use that as well. We have things like AutoGPT, which automatically breaks down into different tasks. And we also have what is called inference time reasoning. So recently we say, when we get a complex question, don't just try and answer it. You can do better, right? You can generate your own synthetic data. You can fetch you can call some external tools and so on. So all this goes into inference time reasoning. That means that at the time when we get the question, only then we do the reasoning, not automatically answer the question. So that's a sort of like, you probably know the book of Kahneman and Tversky, Thinking Fast, Thinking Slow. So that's like the system 1 and system 2. So system 1, use just internal knowledge of LLM, hallucinate, but get the answer really fast. So this inference time reasoning basically it says, try to get more information, try to be reasonable, try to be rational, and only then, when you have reasoned, only then you can produce the answer. So that would be like analogy with the system 2 of the Kahneman and Tversky. So we also have recently many what is called agent architectures. So let me maybe show just the agent. So it's a relatively new approach which tries to, I would say especially the companies are really interested in that aspect. So what do they do? So they say, okay, I have this user request or task. So, and I have an agent. So agent analyzes my request, the input request, and then decides, it makes a plan how to solve it, and then it can store the intermediate results in the memory, and it can also call external tools. So all this makes it much more powerful, right? So, so we can use these agents to automate scientific tasks, administrative tasks, so many different tasks. And it's right now, it's one of the hot topics in the industry, and many companies are trying to, let's say, automate their administrative tasks with that, right? Hoping to, of course, reduce their workforce as well, right? Okay, so if I mention also some of the agents for science. So in the science, we have one of the most complex pipelines. So, but many of these pipelines can be automated by using several let's say, coupled LLMs, which are trained and adapted for specific tasks. That means instead of using the same LLM, which would just answer the question, we say we have one LLM to analyze the query and another one which will generate the code, which will go call external tools and so on, right? So that's the idea. So we have one example which was done in our project, large language models for digital humanities. So Kaya Dubrovec is the leader of that research. So here was the idea to make an agent for grammatical analysis. So that means that if we get the linguistic question, like for example, what's the order of subject, word, and object in the French language? So what we do, we have a LLM which analyzes this question and maps it to the sentence level task. That means it said, okay, go into the database where the sentences are labeled. Let's say in the linguistic there's a database called Universal Dependency where the sentences are labeled with order and so on. Go into that database, so it generates the code, and LLM would generate the code for that, basically a Python code. That Python code is executed and then it's tested on different sentences. And for each sentence we get a different word order. For example, subject, word, object, and maybe no answer in this sentence because for some reasons and so on. And then when we have these results, we use another LLM which will aggregate these results. So for example, it would count how many subject word orders we noticed or how many, I don't know, subject object words we noticed. And then we produce, for example, the answer, so the dominant word order, but also the detailed distribution of different sub-answers. We could also go a step further, write the graph, construct the graph, write a piece of text on that, whatever, right? So that's the, let's say, a sort of new step in the methodology to scientific research. So what LLMs enable us, they enable us to automate fairly complex pipelines, right? So that's the idea, what we want to do. And as researchers, this is the things we want to do in digital humanities. So yeah, what we want to do, of course, this is not just subject, word, and order. The order of sentences we want to answer basically on any linguistic questions or almost any linguistic question. And we want to basically make a system which will not use just one database, but several databases and so on, right? So yeah, let me also mention another of our, let's say, development, which I think everyone who works on Slovene could be interested in, and that's GAMS, so the generative model for Slovene. This is one of these open source models, sovereign models for Slovene. So many, let's say, many languages try to build their own large language models. Because why? Because they would work better for this specific language than compared to, let's say, multilingual models which work on hundreds of languages. These are specialized for one specific language. They still pretty well cover also other languages, but they are still specialized, for example, for Slovene. It's open source. That means that for many purposes that's important. It is all the data you use stays on your machine, so it will not go somewhere in the cloud. So for example, there are lots of reasons why this would be useful, right? So for example, in medical, you don't want to expose your medical data to the cloud. You're not allowed to. Let's say in the law, in the medicine, in the public administration, there are lots of cases where you should not basically put your data to the cloud. And besides that, the fact that it's open source, it also guarantees that you know what was put inside the model, right? So that is transparent, right? So we have now different models of this GAMS model. So 9 billion model parameters, 27 billion model parameters. We also have the third generation of that model. For its training, we use quite strong supercomputers. So for example, Slovene Vega supercomputer wasn't sufficient for that. So we got some time on Leonardo Booster, high performance computing machinery. And yeah, so what we did, we basically did continuous pre-training on Slovene data. We took Gamma 2 as the baseline or Gamma 3 as the baseline. and we used around 8 billion, or in the first version, and 70 billion parameters, 70 billion tokens to train that model, to specialize it. That's a huge amount of data, right? So we have different sizes of that model. The smaller one would fit on relatively modest devices, on personal computers, but the larger one would need, again, supercomputers for their, or at least very good GPU computers for their execution. So currently it's the best open Slovene large language models. So we also built the benchmark so that we can compare different large language models, how they perform on common Slovene tasks. And as I said, this GAMS tree, which was released in December, it's even better. We are still improving them, and it's, for example, in recent testing, it was showed that it's best for at least 20 European languages. So it's not just for Slovene, it also works very well for other languages as well. So for example, here's the benchmark. So it shows that, for example, on the machine translation, it was really the top model, for example. Okay, so how do we build such models? So if I illustrate that, so in the first phase, we do language alignment. That means that we continue this pre-training, predicting this next word, but with the text which are aligned, which are, one part is in English and another one is in Slovene. So basically the LLMs aligns the representation for the Slovene and for the English text. So in the second phase, we use high quality Slovene data, for example, Wikipedia and let's say standard corpora of Slovene. We also use the corpus of academic Slovene, that means all the PhD thesis, master thesis, and bachelor thesis. And for example, we intentionally skipped web crawl and tweets, and we sorted the news by increasing time, so that the older data was overshadowed by the new one. Right? So all this helped to improve this, let's say, little tricks help to improve the quality of the GAMS, which is, as I say, now the state of the art for many Slovene tasks. So, for example, on the settled benchmark called SuperGLUE, so Super General Language Understanding Evaluation, so many tasks, and we see that this GAMS variant is on top of the leaderboards. So all this we are doing inside the project Povejmo, which basically tries to build large Slovene language models and also tries to help, let's say, a few selected use cases from the industry to make good use of Slovene LLMs. Yeah, so we can see here that in this size of the model, this is the top performing right now across many European languages. So one of the things we also did, and which is which is useful, is so-called LLM Arena. So that's basically, we want to get this feedback about the model response. If we want to align the model with the human preferences, we have to know what the humans prefer, right? So what we do, we pose a question, for example here, kakšen je postopek gradnje velikih jezikovnih modelov za jezike z manj viri, and then we ask this question to two LLMs. They generate their answers, and then the user, any volunteer, basically can respond, I prefer this answer, or I prefer this answer, right? So we collect these answers, and then based on these answers, we align new models. So the user doesn't know which of these models is answering the question, but it turns out that according to this, let's say, human evaluation, basically our GAMS model is just a little behind, let's say, the 1,000 times larger professional Gemini 2.5 Pro. So yeah, I would urge you all that you can test this yourself on the Arena website, right? So always there are, not just our models, but also some state-of-the-art models, because we want to have comparison how good they are doing and what really the good answers should be. One of the possible answers is also that none of the models is good, or they are both good, right? So this leads us to the question of how can we inject different knowledge into large language models. So especially for some scientific research, this is what we want to do, right? So we know that LLMs by themselves, they hallucinate, they are not reliable enough. So we as an expert if we want to use them for improve our methodology, we'll have to inject some additional knowledge. So, and there are different ways how we can do it. So I'll show you one example of our research, what we do. You're still okay with time?
Yeah.
Okay. We built the data set for common sense reasoning. So what is common sense reasoning? So let me show you an example. No, okay, I don't have it here. So for example, in common sense reasoning, what we do is we have, let's say, for example, a sentence. Let's say a man and a dog. A man walked his dog down the street, and then the second sentence would be the neighbor came and offered him a bowl of water. Now the question is, who was offered the bowl of water, a man or his dog, right? So we humans, we tend to know that, right? Because we know that a bowl of water is typically not offered to a man, but to a dog, right? But it's not necessary that the machine, that LLM would know that, right? So, but we want that this sort of common sense would be injected into the LLMs. So, so there's a task for doing that, and we basically built a Surveying data set of this type of knowledge. So we also provide the explanations. So, for example, what's the reason that the bowl was offered to the dog and not to the human? So, for example, it could be some convention. It could be, let's say, physical laws. For example, you would say, if I take this mouse and drop it, whether it will fall to the ground or not. So there are many reasons why this, what we call common sense reasoning, works, and we provide these explanations. And it turns out that if we train the LLM with this additional knowledge, they also know better to solve new cases and also to explain their behavior better. And this is one of the things we are, as researchers, we are interested in. We are interested in these explanational aspects because we think that in many sense, we cannot just trust LLMs, right? So we have to also train them so that they will be able to rationalize and to explain their behavior. This is definitely a difficult task, even for humans, right? So we cannot always explain our thinking. Sometimes it's subconscious or just too difficult, and we have to explain it on different levels. For example, a different explanation for kids, a different explanation for experts, right? So all this makes this, I think, a tough problem, right? So anyway, we are trying to do that, and we are injecting this knowledge, for example, in GAMS models. We are also working on a data set with ethical norms with the colleagues here from the Department of Philosophy and Department of Theology. And basically, we're trying to build new application based on GAMS, for example, grammar error correction. We have already built a very good machine translation tools, which is freely available, models for summarization, simplification, and so on. So, yeah, as I said, GAMS3, which is currently our state-of-the-art model based on the freely available geometry. We are currently adapting it to be able to handle images, but also that we'll be able to call external tools, go on the internet, call some programs, and so on. We built a data set for reasoning, for the mathematics, and also for understanding, let's say, numbers in tables and so on, equations. So yeah, but let me go now to my sort of, the second part of my title was about the evaluation, right, on the analysis. What we can do if we want to analyze things with large language models. So once you start doing that, when you start to use LLMs in your research, then as I said, you're basically moving to the empirical science, right? And this one has certain specifics, right? You will have to evaluate your result. You will have to do some statistical analysis of your results. So in principle, LLMs can answer any question, right? So they are not trained to abstain from answering, right? So they will just answer whether it's correct or not. So is it correct? You don't know, right? So, but if you want to use that in your research, right? And if you want to analyze, let's say, thousands of texts in your database, then you have to know how good it's doing, right? Even if it's not perfect, maybe you are sufficient to do statistical analysis, but still you have to know it as a scientist, right? So, for example, here I have an example from the lexicography. We are working with the lexicographers quite a lot. And so, for example, you see it's quite a complex prompt, it basically instructs the LLM to write a definition for the dictionary of Slovene, right? And it gives it some examples and tell you where you can get this data, separated by sense and so on. So altogether, quite a complex task. So will the answer be correct, right? So that's the question. Is this useful? So yeah, so we have upfront, we have no guarantees, and we have to do some empirical analysis to see if this will work, right? So yeah, so for example, we have done these types of analysis on many problems. For example, in the news analysis, in the articles, scientific articles, on the folk tales and so on. So it can be done. It's not a problem, but yeah, we have to know a little bit of the methodological background here. Okay, so how do we verify these LLM outputs? Let me just give you a few, let's say, hints. So if we use LLMs for complex questions, so our procedure will be such as we will first ask LLM, and then we'll have to verify the answers. Even if later, when they are verified, we will use them on millions of articles, we first have to know how good they are doing, right? So if the accuracy is high, okay, let's use them, and we will report maybe the accuracy, the standard deviation, and so on. But if the result is too low, well, we shouldn't report that in a scientific paper, right? We should basically go back, revise, maybe fine-tune the model, collect more data, like the standard scientific methodology. But in the verification, we have at least three parts. Let me explain them. So first, we could ask humans first and compare our LLM results with what is called gold standard answers. So that answers which were verified with the humans upfront. So that seems pretty standard approach. Of course, the problem is that getting human experts to answer complex questions is not that easy, right? So we have to collect that, and it would take some time, maybe also money. The second is that we can ask humans to verify the answers of LLMs. So that works to some degree, but it's time-consuming and slow, right? So yeah, we can do it, and it's a little bit lower, right? So humans, if we ask them, do you agree with this answer, right? So there will be a lot of, let's say, things which might be implicitly overlooked. We just shallowly check the correctness, and they say it's true or not. But maybe if we have to invent our own answer, it would be more complex, right? We would think of many more things, right? So this verification is not as good as compared with golden standard. And the third way is what is called LLM as a judge, right? That means let's ask possibly a stronger LLM to answer this question and then compare the results. So is it a legal way or not? I mean, is it a fair and sound way? So if LLM is really good at that, then maybe we can do it. But we have to verify the LLM one way or another anyway, right? Otherwise, we will go into circular argument, right? So we don't want that. Okay, so if we go into this first verification path, so that means we compare the human gold standard answers. So it could be time-consuming or expensive to get these gold standard answers. But for some tasks, like, for example, classification, if we just ask, let's say, classify this text according to the sentiment, whether it's positive, negative, or neutral, we can have some automatic statistical metrics like accuracy, F1, precision, recall, something which is in the standard repertoire of natural language processing. But in contrast to classification, if we want to compare, let's say, generative text, this is much more difficult, right? So we don't have just three classes, positive, negative, neutral, but we get the answer. For example, if the task is, let's say, write an essay, right, or summarize. So comparison is much more difficult. It's not just a single number. So, but yeah, we have some measures. For example, NLP has produced some standard metrics comparing the lexical similarity with n-grams. So some measures like BLUE, rouge, and so on. Then we can use what is called sentence encoders. That means we use another LLM which encodes both answers, the gold standard and the newly generated, and then compare the similarity in the some embedding space. This works to a reasonable degree. And then again, we can use LLM as a judge. At least what we would expect here, that we have stronger LLM, which has to be verified first, and potentially we are still in the troubles because we are making the circular argument here. So the second way of verification is human verification, right? So I mentioned, yeah, it's a good way, right? We can, beside the correctness, we can also check for style, format, consistency. So yeah, a good way, but time-consuming, yes. And anyway, it's a weaker form of verification, right? Because, for example, we can be primed by already seeing the correct answer. The answer of the LLM. So the third question is about reliability. So if you want to make it a good scientific, let's say, methodology, it also has to be reliable, right? So what we have to provide is, for example, variance in the answers, and there's a huge sources of variance. So when we get human gold standard answers, human might not be consistent always. So for example, if we are asked the same question twice, we might produce different results. Or if we ask different humans, they might produce different results. For example, for the sentiment, which I mentioned a few times already, it is known that if we ask humans about the sentiment of, let's say, tweets, the agreement is only around 70%. So it's not perfect, but it's huge difference. And if the question is more complex, for example, if they ask them about the values in certain text, then the agreement is lower. It's maybe 30%, right? So yeah, and also LLMs. LLMs are also not consistent always. So they are basically probabilistical generators. They do not produce the answers always the same answer, because they are intentionally instructed not to produce always the same answers, right? Because we want to have more varied output. And for humans, there are different reasons for that variance. Let's say sense of humor, mood, education, and so on. And for LLMs, we could use different prompts, different LLMs, different parameters, instructed them how to do it. We call these temperature parameters and so on. So yeah, but if a good practice here would be still that we report this variance, we first compute this inter-annotator agreement. So we ask several humans at least part of the questions and check how consistent they are in the answering. And we also compute self-agreement, right? So we ask a few questions to, let's say, the same annotator twice and check whether how consistent they are, right? There are some standard statistics like Fly's kappa, and we can see how good we are doing in statistical terms. Right, so there are standard ways from the empirical sciences. How can we improve this reliability? We can repeat, we can average, and yeah, we should show the variance so that people would know what we are talking about. The question is also about reproducibility, another scientific concept from the empirical science which we have to follow here. And it concerned, we should know that basically research in LLMs is very fast. So for example, if you are using, let's say, ChatGPT in your research, this is not the same ChatGPT which you used 1 year ago. It's a new version, right? So the results will no longer be reproducible. So that's also one of the reasons, these commercial LLMs have around a lifespan of around a year. And it's a huge problem for any scientific research which does that, because it's no longer reproducible, right? But yeah, as I said, yeah, question? No. There are many, let's say, less capable open source, less capable, they're 1,000 times smaller, open source models, and they can come handy and help us in that respect, because they will always be around, because they are freely available on the servers, and we can run them on our computers. Right, so let me show you one use case, how we approach that. So there was quite some complex question in folkloristics, and example how we evaluate this is LLMs. So in folkloristics, one of the problems is motif detection. So motif is, let's say, something which is a sort of a standard, let's say, a standard theme or standard pattern in certain story. It's called motif, right? So we did this study with Professor, my student, PhD student Jascha Archon, and Professor Polona Tratnik here from the Faculty of Arts. So we did analysis on the Cinderella stories as a case, as a use case. So basically, Polona Tratnik collected, let's say, a few hundred Cinderella variants. I never imagined that there are that many, but yeah, they are. So, and then the question was, can we develop a methodology for automatic detection in these motifs based on the LLM? So, for humans, it's a tedious work. So, checking a few hundred, let's say, Cinderellas for, let's say, 20 or 50 motifs, it's a repetitive task, right? So, yeah, and motifs are like, for example, crew, stepmother, glass shoes, helpful birds, and so on, right? So, and the question was, first questions we try to verify, can LLMs answer this type of question at all? So for this, we took, for example, 13 Cinderella variants from different parts of the words. I mean, the text was in English. And then we took motifs from one of these, let's say, ATU is one of the tail type. So one type of the let's say, stories in the folkloristics. And we manually labeled 15 motifs, right? And then we checked how good LLMs are on the same labeling. And for these 13 variants, the accuracy was like 89% correct, right? So it seems that LLMs did correctly recognize the same motifs as experts did. So we took that this is good enough so that we can do statistical analysis. And we did it, right? So next we do, okay, so yeah, what we used, for example, 77 variants from 5 continents. And then we also had, in the Polona Tratnik collection, there were also 33 Slovene variants which were not previously analyzed. So again, I didn't know that we have 33 Cinderella variants in Slovene. But yeah, so we used GPT 4.5, and we used a simple approach with no additional examples, so-called zero shot. So this was, for example, quite a complex prompt. So for example, again, helpful assistant, you're trying to find different motifs, and these are the motifs which you try to find, and so on. So quite a complex prompt, right? As I said, in 98% it agreed with human labeling. So we produced a table like this. So for each of the Cinderella variant and for each of the possible motifs, we checked the answer of different LLMs, right? And based on this table, we say, okay, these are, for example, the motifs. So we used 3 different variants. One was original from the ATU index. One, we added a few of them which seemed to be necessary. For example, instead of stepdaughter, we said, okay, it could be stepson as well. And then we tried to generalize a few of them. So instead of cruel stepmother, we checked whether there are some cruel relatives and so on. So some different variants of this. And then we've tried to find groups of similar folktale variants. The task, how to do it in machine learning, is called clustering. So we make groups of similar objects based on their similarity. And we tried different, let's say, different types of motifs. And because we wanted to visualize the result, we also used the, let's say, downsampling of the data space. So if we have 18 motifs, that's basically 18-dimensional space. So if we want to visualize it, we need 2 or 3-dimensional space. So we used the dimensionality reduction algorithm called UMAP, and then we produced basically groups of stories in the graphs like that, right? So for example, for 15 specific motifs, it turned out that there are 2 large clusters. For some other collections, there were more. So for example, if we compared different Slovene Cinderella variants, so they were, let's say, one group was mostly about slippers and shoes and clothes produced by magic, and the other group was more about stepmothers and heroin and so on. So yeah, Slovene basically mostly come to this group, but 4 of them also fall